Good morning, students. Today we shall learn the constitutive law. At this moment, we are assuming that you all know the concept of stresses, and you all also know have learned how to measure the deformation, that means the stress. So, in this lecture, we shall learn how the stresses, the internal force intensity that interacts with the non-dimensional quantity, the strain. This lecture, we are going to cover the following topics. First, the background. Second, the conservation of energy, first law of thermodynamics. And then we shall introduce the concept of strain energy. And we shall finish this lecture with the generalized Hooke's law. Now, as you recall, the first lecture when we tried to introduce the concept of stresses, there we talked about the continuum body. That means the three-dimensional body where the material is distributed uniformly over the entire body of body of interest or the domain of interest. Okay, and we assume the continuous distribution of matter. Okay, we did not respect the crystalline structure or the molecular structure or the discrete nature of the body. Okay, same thing we have done in the case of the strains when we learn the strains. Now, if we go back and if we try to see the crystalline structure, then let us see what the existing theory is giving us. Okay, so if we have the continuum body, let us continuum body which is three-dimensional in nature, and we scoop a very small portion where the crystalline structure is visible, say. Okay, if we enlarge, we shall see the arrangement of atoms, and the distance between the atoms are the Rm. Okay, so that we say that it is the equilibrium distance. That means this molecule here. Let me change the color. Okay, this molecule here, it is in equilibrium. That means the attractive force or the repulsive force, okay, they balance each other. Now if you displace any of these atoms, say uh, from its equilibrium position to say this position, okay, we are displacing this atom from here to from the red color position to green color position. What happens? This guy, it is going to encounter the forces, interaction forces from its surrounding, its neighboring particles or the points or the atoms. Okay, so if we consider the first layer, there will be repulsive force. If we consider the opposite one, it would be attractive force. Here it is also attractive force. So attractive force, and this would be repulsive force, attractive force, and attractive force. Okay, so if we just draw this atom here in an isolated manner, we shall see that it is, oh sorry, a force is acting on this particle. I forgot to mention one more. Let me redraw it. And this side attraction, this side also attraction, this side also attraction. Okay, so you can see that it is subjected to concentrated force, all are concentric. So and the resultant of these forces, they are that is different from zero. So that means it is away from the equilibrium configuration. Okay, Now if we just check that, okay, these are the forces that is acting on the particle or the atom which is displaced from its equilibrium position. Now the distance between the atoms, if we consider that to be r, then the interaction energy potential, okay, so that is expressed like that, no, 4 times epsilon within the third bracket, sigma over r power 12 minus sigma over r over 6. There are several choices, okay. This is one example, okay, which is considered by the physicist when they consider the crystalline body, okay. Now if we plot this interaction potential versus this distance, then we are going to have this kind of curve. The one part is left, another is red color, another part is blue color, okay. So I just wanted to show the red color zone you get the repulsive force, and the blue color zone you are going to get the attractive force, okay, and equilibrium position can be identified here, okay. So now if we measure the displacement from the the equilibrium configuration, then instead of r we can say that, okay, let us consider the displacement, because in our previous lecture when we learned the strains, that time we have considered the displacement from the equilibrium configuration. So if the displacement or the deformation is 0, then the interaction potential is taking its minimum value, and if you just shift this one atom uh, with respect to the other such that the distance between the atoms are getting reduced, then you are going to get the repulsive force, okay, and the blue color zone you get the attractive force. Now interaction force is defined as the gradient of this interaction potential with respect to this r. Now if we just assume that r is measured as, sorry, this r is measured as Rm plus u, okay, then we can define u as the displacement as the difference between the current distance minus the equilibrium distance, okay. And if we try to approximate this interaction potential at any distance away from the equilibrium configuration, then usually we all know that if we are going to expand using the Taylor series, then we get this kind of series expression. Now respecting the interaction force versus the potential expression, that means the gradient of the potential with respect to distance is the force. So one can identify that the gradient of this interaction potential measured at the equilibrium configuration, that is 0, because this equilibrium configuration, nobody's the resulting force is 0, okay. So if we drop this term, then we are left with the first and the quadratic term. Now if we calculate the force, interaction force at the deformed configuration, what we get that, okay, this is the curvature of the interaction potential times the displacement u. So this curvature is measured at the equilibrium configuration, so that is a constant. So it is exactly taking the form as if it is a spring with a spring constant k, which is d2 phi dx2 evaluated at r naught, okay, or u0, okay. So this is the verification, okay, that, okay, in the neighborhood of the equilibrium configuration, it is following the simple uh, the string like behavior it is showing, okay. So that means force is linearly related with the displacement. So this is the background, okay, this is the background which we are going to follow for the continuum body. Now if we perform if we take a sample a specimen rod, okay, if we consider a rod, that means if we are going to consider the uniaxial test of a mild steel bar, and this you would be performing in your third year laboratory course. So this is the gauge length, this is the gauge length L naught, and you are just applying the force P. So this entire sample is going to get elongated. Now if we draw the force versus the elongation, that means if the initial length is L naught, and at level P it is taking L, so U equals to L minus L naught if we define, and if we keep this one U along x axis and P along y axis, we are going to see that it is going to give us this kind of diagram, this brown line. So it shows a almost linear relationship up to the point 1. Then at point 2, what is happening? It is going to 1 to 2, it is going to follow a curved path. Then at 2, near about 2, all of a sudden, with a very little or no deformation change, the load level, the force level is going to drop from 2 to 3. Then we shall observe that the increase in the deformation without any changes in the P up to the point 4. So we shall not observe any increase or decrease in the load value P from 3 to 4, and beyond 4 again we shall observe increase of the load P with the increase of the deformation U, displacement U, and up to the point 5. Okay, and after point 5 we shall observe sudden appearance of the neck or the reduction in the area, and at point 6 the material would be split into two parts. Okay, so it is the failure point. So point number 1, this is the original O to 1, that is known as the zone of proportional limit, or it shows the linear elastic behavior. Then 1 to 2, it is the non-linear but the elastic. That means if you start unloading, it is going to follow this path, the old path again. Okay, the point 2 is known as the upper yield point, point 3 is known as the lower yield point. 3 to 4 is the flow zone, that means it shows the completely plastic behavior. Okay, and within this zone, if you start unloading, it is going to follow a path which is parallel to the initial tangent, and you come back to stress free configuration, which is different from your original configuration. That means there will be the permanent deformation after the removal of the load. Again, if you start loading, it is going to follow this path, and it will come up to this junction, then it is going to follow the old path. Okay, so beyond point 4, we say that it is the point 4 to point 5 with the level 4 to level 5. Okay, that is the strain hardened zone, and if you start unloading at any point within this zone, you are going to get the again a path which is parallel to the initial tangent. So, and you observe the permanent deformation which is larger than the previous one, and again if you start loading, it is going to follow the same path, and you get the previous path after this junction. So point 5 is known as the ultimate load, and after point 5 it is the appearance of neck formation, okay, is observed, and the material failure you observe at the point 6. Now here in our course we shall go into the 3 to 4, that flow regime, okay, when we start discussing the failure theories. But the constitutive law, we are going to limit our discussion within the first zone, where first part, where it shows the perfectly linearly elastic behavior. Okay, so that is the sample, and we are interested to see what is happening in the first part. The slope of the stress strain curve, which is basically with respect to our consideration, we say that this sigma equals to P over the cross sectional area A, and this is the elongation, okay, the elongation delta over the initial length, that is the measure of the strain, okay. The delta is the elongation of the sample at the load level P. L is the original length, gauge length. L is the original length, not, and the cross section area A naught, A naught. Okay. So if we stick to the first part, we see that okay, it shows a linear relationship between the linear relationship is valid up to the point 1. That means the highlighted part. The slope is known as the Young's modulus, and stress is expressed in terms of the Young's modulus and the strain uh, by this relationship sigma equals to E times epsilon, okay, which is the simplified version of the celebrated Hooke's law. And for homogeneous material, okay, we assume that E is not going to vary from one point to another point. That means everywhere, if you sample at any point within the domain of interest, you are going to get the same value of E. Okay. Now let us consider the elementary body, okay, this cube, okay, of dimension dx, dy and dz, and here if we assume that this small differential element is subjected to the axial force P along the x direction, and because of that the sigma xx is getting developed, where this is the px over dy dz, okay. So only sigma xx is alive. So due to that, it is going to deform, and the deformation, the change in the length along x-axis is different from y-axis and z-axis, and we assume that okay, due to that, see epsilon xx, epsilon yy and epsilon zz, these are the direct strain along the x-axis direction, y-axis direction and z-axis direction. They are different from 0. Now, following our definition of strains, one can measure the length, deformed length along x-axis, which is 1 plus epsilon xx times dx, and the y-axis direction 1 plus epsilon yy times dy, and along z direction the 1 plus epsilon zz times dz. Now, using the simplified version of Hooke's law, one can calculate the amount of epsilon xx as sigma xx over E. Okay. However, at this moment we do not know the direct strain values epsilon yy and epsilon zz. Okay. So this problem, there was a proposition by S.D. Poisson in 1828, who proposed that the epsilon yy and epsilon zz in this case would be dependent on the epsilon xx, okay, and the dependency is shown here, okay. The ratio between the lateral direct strain to the longitudinal direct strain, that is constant, okay, and the constant value is minus nu. So minus sign is accounting for the contraction, opposite direction straining, and the nu value is a material parameter, okay, and this is known as the Poisson's ratio. So therefore, respecting the Poisson's observation, epsilon yy and epsilon zz can be computed as minus nu times epsilon xx and minus nu times epsilon yy. Now, if we substitute the value of epsilon xx in this relation, then what we shall get? We shall get the following relationship: epsilon xx equals to sigma xx over E, epsilon yy equals to minus nu times sigma xx over E, and epsilon zz equals to minus nu times sigma xx over E. So if we write in matrix form, then we shall get epsilon xx, epsilon yy, epsilon zz as 1 over E or sigma xx over E times 1 minus nu. Similar exercise if we perform along y direction and the z direction, then we shall get this relationship. Okay, epsilon xx, epsilon yy, epsilon zz along the y direction when we are doing, then it would be sigma yy over E. We are assuming that only non-vanishing direct stress is acting in the y direction, and Poisson ratio would be appearing for the epsilon xx, 1 for the epsilon yy, and minus nu for the epsilon zz. And if we repeat the same experiment along the z direction, again we are going to get the similar expression, only 1 and the nu, the placement would be different, and the, the first coefficient would be sigma zz over E times minus nu 1. Okay. Again, we shall assume that the deformation is very small, strain is very small, so superposition is valid. Now let us see what is happening when we have all the stresses which are different from 0. That means we are going to consider a situation where the small differential element is subjected to x, y and z, sigma xx, sigma yy, sigma zz. Opposite direction, the other forces, the equal amount sigma xx acting, yy is acting here, sigma xx, sigma zz, sigma yy. Okay, these are acting. Okay, so for this case, we shall see that the amount of strain can be calculated as a combination or contribution coming from sigma xx, sigma xx, sigma yy and sigma zz. These three relationships they are written in a compact manner using this matrix representation, where you can see that the first column is the contribution coming from the sigma xx, second column is the contribution coming from the sigma yy, and the third column it is the contribution coming from the sigma zz. This is known as the compliance relationship. Okay, so we are assuming that this nu and E, they are not sensitive with respect to the direction change. Every direction, every point, they are having the same value. Okay, and this sort of material is known as the isotropic material. Okay, and if this is the compliance relationship, that means strain stress relationship, then the inverse relationship is known as the constitutive relation. Sigma xx, sigma yy and sigma zz, they can be identified as the E over 1 plus nu times 1 minus 2 nu times the big matrix 3 by 3 matrix times the strain. Now naturally you can identify that this relationship won't be giving any meaning once you once the Poisson ratio nu takes these values. Okay, so the Poisson ratio, if it hits the -1, if it takes -1, then it becomes unbounded, so you don't get any meaning out of that. Same thing is true when you have the Poisson ratio half. So that's why we say that the meaningful value for the Poisson ratio is bounded. Okay, is bounded. When it hits the value half, then we say that it is incompressible. Okay, we shall I think we have discussed that. Okay, the volumetric deformation. Oh no, no, we did not do that. We are going to get this, see this one today. Okay, today. So we shall see that, okay, the meaningful, the realistic value uh, is limited to this zone. Okay, at this moment we assume that it is lying in between these two. This is a mathematical statement. Okay, from this, in order to make this relation meaningful, we need to satisfy this condition. That means the Poisson ratio cannot take any arbitrary value. It should lie within this zone. But in reality, we shall see that it varies from 0 to half. Okay, and we assume for the shear part that it shows the proportionality, where the sigma xy, sigma yz and sigma xz, they are proportional to the strengths gamma xy, gamma yz and gamma xz, and the proportionality constant is g. Now if we identify that, okay, what is the relationship between the g and the other two values e and nu, at all, is there any relationship between them, or there is something? Let us try to check. And before doing that, what we are going to do, we are going to set this condition sigma zz equals to 0. Now sigma zz if is equals to 0, if you see, if you take the last relationship, okay, last relationship, so which says that sigma zz equals to E over 1 plus nu 1 minus 2 nu times nu epsilon xx plus epsilon yy plus 1 minus nu times epsilon zz. If we set it to 0, that implies that epsilon zz would be minus 1 minus nu over, sorry, minus nu over 1 minus nu times epsilon xx plus epsilon yy. So it gives us the constraint, right? The sigma zz0 is the internal constant which enforces the epsilon zz to be a function of epsilon xx and epsilon yy. Naturally, this statement, that statement equals to 0, involves three independent quantities, epsilon xx, epsilon yy and epsilon zz. Okay, so therefore one out of these three variables can be eliminated in terms of the other two, and this time we are selecting epsilon zz, okay, as if it is a function of epsilon xx and epsilon yy. And if we substitute in the first two expression, we shall get the modified relationship between the stresses, direct stresses sigma xx and sigma yy, and the direct stress epsilon xx and epsilon yy. Okay. Further, if we said that, okay, all the other stress components are 0 and epsilon zz is not equals to 0, that can be verified. Already we have seen, no, that epsilon zz, it is minus nu times 1 minus nu epsilon xx plus epsilon yy. Naturally, epsilon zz 0 is possible once you set the Poisson ratio nu to be 0, or the sum of the direct stresses epsilon xx and epsilon yy to be 0, which leads to the trivial situation. And the Poisson ratio 0, that is also a special case. Okay. Now we have got the relationship between the sigma xx, sigma yy and epsilon xx and epsilon yy. If we recall the transformation relationship between the stresses and the strains, you can see that we had this kind of relationship when we change the coordinate axis from xy to x prime y prime, and this relationship for the strains from xy axis to x prime y prime. Now if we set the theta to 45 degree, then we shall get the following relationship, that sigma x prime equals to tau sigma y prime equals to minus tau, and sigma x prime y prime equals to 0. Okay, this we are getting where with respect to xy we have considered only the shear stresses. Okay, pure shear, pure shear, and 45-degree rotation we are getting the direct stresses. Okay, that you all know, right? That if we recall the Mohr circle, and if we have this diagram only pure shear, that means the shear stress values are here. This is the plus tau, this is the minus tau, and here is the okay, this is the other direction, the other section x plane y plane. Okay, so if we get this one, so we see that 45 degree, that means 90-degree rotation, we are going to get the direct stresses taking the same magnitude tau. Okay, and if we just consider this square small differential element, and if we consider only the shear deformation, we see that one diagonal end is O, another diagonal end is P in the undeformed configuration. This phi bar is going to take the deformed configuration represented by O and P prime. Okay, this deformation, deviation from 90-degree angle is the measure of shear angle, we all know. Okay, it is very small, that's why we are just considering a small right angle triangle, okay, by rotating OP phi bar, okay, such that the P coincides with P1. That means this red line is orthogonal to OP prime. Okay, so this angle is very small, that's why this the radial line and the tangential arc, they are normal to each other. Okay, and using this triangle we can measure, okay, how much is the distance between the P1 and the P prime. Okay, and we know the side length, so from P prime this length is A times gamma. If the A times gamma is known, and if this angle is 45 degree, then we see that the this P1P, that would be A times gamma over square root of 2. Okay, and the initial length is A times square root of 2. So naturally the direct strain along the diagonal direction, that means epsilon x prime, which we have considered 45-degree rotation. This is the xy, and this is the x prime and y prime. So this is 45 degree, this is also 45 degree. Okay, so along that direction we are going to get this direct strain, that means one of the diagonal is getting elongated, the other diagonal is getting contracted, okay, shortened. Okay, so the stretching is gamma over 2, and the strain in the other direction is the minus gamma over 2. Okay, that means it is going to get shortened, the length is going to reduce. Okay, so now if we try to use the our constitutive law which we have got after setting the sigma zz equals to 0, we see that the direct stresses values after transformation, whatever we have got, we have substituted here, and we see that okay, it is becoming something that tau equals to E over 2 into 1 minus nu square times 1 plus minus nu gamma. So that simplifies to E over 2 into 1 plus nu times gamma. Earlier we assume the relationship between the shear stress and the shear strain, okay, such that the proportionality constant is accounted or the represented by the G. Now, after doing this exercise, that means considering the two-dimensional problem, and after 45-degree rotation, what we see that the tau and the gamma, they are related via this relationship, where the proportionality constant is nothing but the E over 2 into 1 plus nu. That's why we say that the shear modulus G is not independent, that can be identified as the E over 2 into 1 plus nu. Now, up to this point, whatever we have discussed, that is basically we assume something at the very beginning, and step by step we try to construct the constitutive law for the isotropic body. Okay. So, following the by the experimental observation and the definition of Poisson's ratio, okay, application of elementary Hooke's law, that which you have learned in your school level, okay, utilizing this thing and utilizing the coordinate transformation, we have got something. We have got something, but we do not know whether this relationship is valid for any general material or not. Okay, so next part we shall just approach this problem from other direction. Before that, we recall the equilibrium of a small differential element. This type of diagram you have learned in your mechanics course. Okay, the equilibrium, the axial force N, the bending moment M, and the shear force V. Okay, so I'm not going to consider the bending moment M and the V, only the axial force, because it is a rod problem. Okay, if we consider this is to for this has some purpose. Okay, so if we just for the time being accept that the equilibrium of this differential element, if we consider the equilibrium along the x-axis direction, where the distributed uh, body force is qx, and in the x direction, and distributed body force in the y direction, y direction is qy, and area averaged area integrated distributed force along the x direction is fx, and along the y direction is fy. And we see that, okay, the in order to maintain the equilibrium along x-axis direction, we need to satisfy, that means the gradient of n needs to satisfy this relationship. This is not difficult to prove if we consider the equilibrium along x-axis direction. If xi equals to 0 means the nx at O with a minus sign, this is O and this is A, OA is delta x, okay, plus nx at A plus fx delta x equals to 0. Now, if we assume that the value of n and its gradient all are available at the point O, then this can be simplified as minus n measured nx measured at x equals to O plus n measured at x equals to O plus dnx dx times delta x plus fx delta x equals to 0. Now, this guy is cancelling this guy, so we are getting dnx dx plus fx times delta x equals to 0. So, as you all know that delta x is finite, it is different from 0. So, we eliminate from both the side. Now, after that, if we set delta x tends to 0, that means we approach to a point O, we get that this relationship is valid. One needs to satisfy plus fx is 0 at O, okay, x equals to O. That is the equilibrium equation at the point O. Okay, so we just assume that we know, as if we know this equilibrium equation. Now after that we shall do something, some exercise. Let us consider the bar which is clamped at the end, uh, left end at O, free at the other end. It is subjected to a concentrated force PR and distributed force intensity F per unit length Fx. Okay, and the point marking, the point 1 is located at x distance away, and that is undergoing a small deformation delta u at x. The end point 2 that is undergoing a small deformation delta u at measured at x equals to L. Now if we wish to express the work done by the external forces, then it reads delta w external as if we are let us try to draw the free body diagram. Let us assume that if we remove the support, the effect of the support is accounted by the reactive force PL, which is not known at this moment, but it is acting at the left end. PR is acting at the right side. So using the elementary concept of the work done, force times displacement, we can calculate the concentrated action of the concentrated force PL times delta U measured at the point x equals to 0, PR times delta U measured at the point x equals to L, and the distributed work done Fx times delta U integrated over the distance from 0 to L. Okay, this we are getting using our elementary idea or definition of work done. Now, if we employ the equilibrium condition at the end, if we assume the existence of the internal force resultant Nx, okay, using the sign convention which we have done in our previous slide, okay, Nx and Nx, okay, this is the positive direction. Then if we consider the equilibrium at the end, what we get, Nx measured at x equals to 0 must be equals to minus PL, and Nx measured at the x equals to L equals to plus PR. Okay. If we substitute this expression, work done expression, then we see that these n values can be replaced by this integral. Okay, this is the identity. Okay, basic identity we have replaced, and then we are if we just apply the chain rule of calculus, or the derivative of two functions, the multiplicative form if we have, then we can split them, right? Delta u times dn dx plus nx times delta ddx of delta u. So first part we are getting something which we know that it is nothing but the equilibrium equation. Okay, so what we are doing, we are recalling that this is basically the equilibrium equation. Now if we say that okay, this delta u is taken about a configuration which is in equilibrium. Okay, so that means this this first term would be 0. Equilibrium means this gradient of n is satisfying this relationship. It is taking the opposite value of Fx, distributed body force. Okay, and the definition of epsilon x, the direct strain, that is the du dx, you all know, I believe. The change, small change due to the virtual displacements, small change in the strain, that is the virtual strain, is like that. We see that the right hand side we are getting nx times the change in the strain. So nx internal force intensity, the strain is also the internal deformation measure, which the integral of this quantity is the taking the same value as the work done by the external forces. So this part, right hand side part, we shall give a name, that is the change in the internal energy. Okay, now if we further define the internal energy density, the intensity per unit length, to be delta the calligraphy q as n times delta epsilon xx, and if we wish to say that it is integrable, that means if it is integrable, if it is u, if this u is a function of epsilon x, then this change in the u must be du d epsilon x times delta epsilon x. So that I wrote here. So if this is integrable, if there exists any strain energy, the internal energy density, okay, then we say that n must be equal to this one, which is the first definition of the constitutive law. That means the internal strain stress, the force resultant, how it is related with the strains. Okay, if there exists any internal energy which is expressed solely in terms of the strains, then we can calculate the stress resultant by taking the gradient with respect to strain. The simplest choice, so therefore you get the total internal energy as the integrated value of the internal energy density. The simplest choice is that let us set Nx to be Ae times epsilon x. Naturally, that implies that U, the density, would be half time Ae times epsilon x square. Now you compare with the spring force. If we have a spring P with a constant k, we all know that that is because that equals to k times x. X is the elongation, and the strain energy, the density for the spring is half time k time x square. Okay, so this is simplest choice. You can take any complicated choice, that is a separate issue, but the simplest choice, the linear relationship, we see that the energy is having the quadratic form. So what is the learning today? We have learned that at equilibrium configuration, okay, near about that, delta W ext is balanced by the delta W int. That means internal change in the energy is balanced by the external change in the work done by the external forces. Okay, this is this is nothing but the statement of thermodynamics. Okay, first law of thermodynamics, which we shall formally